Well, here we go again. One more time, you guys. I wanted to give you a little bit of a heads up of, if I can move this out of the way, a little bit of a heads up of exactly kind of where we're going from here. I think I mentioned to you guys that we got information from the College Board about how they're going to adjust AP exams, and I think I mentioned to you basically they're cutting off the curriculum where at the point where most teachers would have gotten to. Um, as far as what's going to be covered on the exam and how they're changing it to be instead of the big 3.5 hour test, there's going to be a 45-minute online test, which is going to be all free response. Not necessarily the same kind of free response. We just don't know yet. We won't really know until April 3rd. Some more specifics about it. But what that means for us is that we are done with all new stuff. We were almost there before we started area volume. We were almost to the point of review, but now I hesitate to tell you this. I wanted to go ahead and take that online quiz on area and volume because that's the last we're going to do with it. We're not even going to review it. It's not on the AP exam. Well, not area between two curves. You know, way back when we first did integration and we talked about basic area, that'll still be on there. And actually, there's a little bit of some of the involved response questions that we practiced way back when we did fundamental theorem that are not going to be on there. So when we review, we'll just kind of cut that part out and review only what is supposed to be on there. So this is going to be kind of our schedule. I'm going to have to kind of change review from what I've done in the past based on this new AP exam. But here we are. So today, in just a little bit, we're gonna do what I'm calling this kind of a jump start of the basics, um, and so it'll just be kind of a quick review of the most basic stuff, and then we'll go into each chapter and we'll talk a little bit more involved in each chapter. Um, I wanted to kind of show you. We'll still be having our online quizzes. I know I didn't list them over here being due on Monday, but we'll still be doing those online quizzes, and we'll still do those, you know, every Monday, and it'll kind of review what we did for that week. But then, as far as grading for this quarter, so we'll have those quizzes, we'll have our daily work grades, and then we will take 3 tests. And I don't want to put them on the calendar because I want to wait and see kind of how things go. But just so that you know, we will end up having a test over chapter 1 and 2, and then we'll have a test over chapter 3, and then another one over chapter 4, and another one over chapter 5. I guess I said 3, I meant 4. So we will have these 4 tests, and they'll be equally weighted. And then when we get at the very end, and we'll do a practice test, and hopefully at that point, I'll have a good idea of what this 45-minute thing is going to look like. And so that practice test will be for a grade also. So it'll kind of be added into this. And so this will be kind of the biggest weight of the category. There is no reason that this quarter shouldn't be, you know, your highest grade yet because, like I said, it's going to be all review. It's going to be kind of me here to help you along the way. So I just wanted to give you a little bit of an idea of what that looks like. All right, so for today, we are going to look at just some of the basics. Now, I was just thinking, I've heard so many teachers talking about how they're hearing from students that, you know, after a little over a week, they're really tired of this. I wonder if this would cure those students who, you know, who tend to be absent all the time. Oh, come on, you know exactly what I'm talking about, and you also know exactly who you are. I just wonder if, you know, being forced to stay home is one of those kind of things where they're like, no, don't make me, I want to go back. I don't know. We'll see. It would be nice for you first period people if it would cure, you know, the ones who like to come in halfway through. But whatever. That's not what this is about, right? Okay. So we're going to start with the basics from chapter 1. And the way this is going to work is I'm going to go through just a little bit of the notes. You're going to complete those with me. and then there'll be a short section that I'll have you complete, and then we'll come back together, compare answers. We'll do a short section on derivatives. Same thing. I'll have you try a couple problems. We'll come back together. Same thing with integration. You try a couple problems. We'll come back together, and then by the time you finish this video, you will be completely done with your work for the day. And I want you to kind of hear from me, like I told you before. My goal for the whole rest of the year in this review is that if you're doing what I ask you to do between notes and homework, I mean, the total amount, my goal is to keep it to be less than 60 minutes each day. So that means, some days it might be a total of 40 minutes, but some days it might be up to 60. But certainly every day less than a total of 60 minutes. So that's less than one full class time. All right, so let's talk about just the most basics. All right, so the basic rules for limits. We said the first thing you should always try is substitution. So let's put here, try this first. I don't know why I thought there should be a comma there. All this distance learning is making me stupid. Okay, so always we're going to do substitution first, and then probably the next thing to look for is factoring, and it's going to be obvious if it's the type to factor. Like a basic example might be the limit as x approaches 4 of x squared minus 16 all over x minus 4. Obviously, you still try and substitute first, but this one, I mean, when you look at it, it's crying out to factor. I mean, it's all I can do to avoid factoring, right, while I'm even talking to you. So that's one that you would factor out and then substitute. When we say rationalize, what we mean by that is rationalize the numerator. Remember, these are the kinds where you obviously first you try and substitute, but then you tend to end up with square roots in the numerator. And like, for example, if you look at number 2 down at the bottom, there's one that has square roots in the numerator, so you would rationalize it. So on those, we said you should multiply both top and bottom. Should I have said numerator and denominator? Multiply both top and bottom by the conjugate. And remember the conjugate. Well, do you remember what conjugate means? Remember, the conjugate is, for example, if your numerator is, how about the square root of 3 plus x? Well, then the conjugate would be the square root of 3 minus x. So you just change that middle sign for the conjugate. Okay, simplify. This type usually comes up when you have a complex fraction. Complex fraction, like a fraction within a fraction, maybe something like, I don't know, 1 over x plus 2 plus 1 over x. I don't know, all over x or something like that you're trying to take the limit of. But in general, it doesn't have to be a complex fraction. Simplify just means if you can't substitute, can you do something to change the form so that you can substitute? Okay, then we had a couple of special trig limits. Remember we said one of those was the limit as x approaches 0. Remember there was one with sine and one with cosine. So the one with sine, right, sine x over x, do you remember what that one comes out to be? Or the other one was the limit as x approaches 0 of 1 minus cosine all over x. Do you remember what that one comes out to be? Yes, I'm sure you guessed it, right? If it's sine x over x, that one comes out to equal 1. And if it's 1 minus cosine over x, that one comes out to equal 0. So those are the ones that you just kind of need to know. They're helpful to get some basic answers. One-sided limits, remember this is the type that might say something like the limit as x approaches 0 from the right of, let's say, 1 over x, right? So if it has that little right or left, that's a one-sided limit. And the thing to these is you don't do them any differently than you do all the rest of these. You follow the same rules. It's just that if none of those things work, this is the type where you might have to then look at the graph And if you have to look at the graph, then that tells you whether or not to look at the left or the right. So for example, if I look at the graph of 1 over x, if I'm coming in from the right, right, that would be this part of the graph. So coming in from the right, um, coming in towards 0, I should say, the graph goes to infinity, right? But if it had said coming in from the left, if it had said x, oh, let me get that out of the way, sorry. If it had said x approaches 0 from the left, so then they'd be talking about this side of the graph of the 1 over x. And as you go towards 0 from this side, it goes to negative infinity. So that's the only time one-sided really matters, is if you have to look at vertical asymptotes. Okay, and then we had definition of derivative. So the derivative of x is the limit as h approaches 0, f of x plus h minus f of x all over h. So the idea here is, if you notice the pattern, then the answer is just going to be whatever the derivative of this part is, right? Because that part is your f of x. And then I'm going to put L'Hopital's rule in here, even though we didn't do it in chapter 1. We just learned L'Hopital's rule, but L'Hopital's rule is for limits. So I'm just going to put it here in this limit section. And when we start doing a bigger review of chapter 1, I'm going to go ahead and include some of the limits from L'Hopital's rule. So the idea for L'Hopital's rule is it's when you're taking the limit of a fraction, right? So you might have f of x over g of x. And it could be x approaches anything. I'm just going to put, a, right? It could be x approaches 2. It could be x approaches 0. It could be x approaches infinity. It just doesn't matter. And so the idea is, if you see that when you substitute, you get infinity over infinity, or if you get 0 over 0, right? That's called indeterminate form. So it has to be indeterminate form. Indeterminate form. So if you see it's indeterminate form, then what L'Hopital's rule says, that you can take the limit of x approaching whatever you had up at the top, but you just look at the derivative of the top separate from the derivative of the bottom. And the idea is, hopefully at that point, you can then substitute. Okay, so here's what I want you to do. I know I did a quick, crash course. So just looking down at these, let's just kind of do a quick look. Remember, always you're going to try substituting first. But to me, some of them, when you just look at it, it's calling out something. Like when I look at number 4, I mean, that's calling out to factor. Or like we said a minute ago, number 2 is just calling out to us to rationalize. I see trig on number 5. I also see trig on number 3, so you have to kind of decide which is which. And there you have your one-sided limit on number 6. So I want you to stop right there and work on all 6 of those. I'm going to ask you to kind of input some information about each of the 6 problems. And once you finish those problems and you've gotten your material in, the quiz is going to pick up again, and we'll start back in on comparing answers to those, but we'll also do a quick crash course on derivatives. Okay, so now you're back, and I want us to compare the answers to those 1 through 6 problems. So let me pull those up. Let's see, how about we look at it here. All right, so here's what I'm going to get for my answers. I'm going to give you a chance to kind of look and compare. I left my work on there, and I, in some cases, showed more work than you really need. So obviously there's an answer. There's my answer. I wanted to show you, well, I'll come back to that. There's my answer. Let's see, 1/5, negative sign. And down here, the answer is infinity, but I also wrote does not exist because, remember, infinity means does not exist. And so I went ahead and left some work in there, like on number 4, I did some factoring. But the stuff that's in green, that was me kind of showing you that you could have just done L'Hopital's rule on those and gotten the same answer. You didn't have to. In the old days, we would have done the blue, but now that we know L'Hopital's rule, if it's indeterminate form and you'd rather do that, it's fine. Like number 4 is just as easy. I actually think number 2 is easier to do L'Hopital's rule. I don't know. Number 5, it's kind of easy either way you look at it. So, if you need to pause to kind of compare and check answers and see what you can figure out, then do that. But try and get all those justified because, like I said, I know it's been a long time, but these are the basics. Okay, um, we just need to kind of get rid of some cobwebs, right? All right, so let's go on and talk about the basics of derivatives. All right, so for the basics of derivatives, the power rule, we don't really call it by name, but let's just go ahead and talk about what the power rule looks like. So the power rule says if we have, let's say, y equals x to the n, right? So that might be x squared, x to the negative 5, x to the 1/2, right? Any power of x, right? Any of those individually. Then remember the derivative, you bring the exponent down in front, you keep the base, and then you decrease your exponent by 1. And I know you didn't really need that. I mean, holy cow, hopefully we can't forget that. But then the product rule, and again, you probably know the product rule, but it's good for us to write out the notation, because I don't know if you remember, but we did a whole lot of problems that were kind of what I called them property problems, where they were like in terms of f and g or h of x, and I think that's a very likely thing to show up on this format of a test. So we're going to say the product rule, if you have, let's say we're told that h of x is defined as f of x times g of x. Okay, so if I want to find the derivative of h, remember it's the derivative of the first times the second plus the first derivative of the second, right? So there's our product rule, and I'm going to kind of go out of order here for a second because remember I've talked to you about comparing that, I guess I'm not going out of order, to the quotient rule. So remember the quotient rule is if I'll define h to be f of x over g of x, then it looks just like the product rule except a minus, right? So I would say the derivative of h is going to be derivative of the top times the bottom minus, so that's the only difference in the product rule, then the top derivative of the bottom. And remember on quotient rule you have to do all over the denominator squared, right? So there's our quotient rule. Again, for the chain rule, I want to talk to you about it kind of as a formula. So here's the idea. For the chain rule, if I have, let's say, h to be defined as f of g of x, and I want to make sure you kind of look at this is different than this, right? Because on number 4, g of x is inside f of x. On number 2 up here, it's f of x completely separate being multiplied by g of x. So this is like when you have a function within a function, and so the derivative is the derivative of the outside but evaluated at the inside times the derivative of the inside. I guess I didn't really need that parenthesis right there. So it's like if you have something like, a quantity to the 4th, right, where the outside is the 4 and the inside is the x squared plus 3, or if you have, like, let's say the sine of 2x, the outside is the sine and the inside is the 2x. So we'll do like a basic chain rule here, but again, don't worry, we're going to develop that a lot more when we get into doing a lot more review in chapter 2. Today is just about the basics, just kind of refreshing ourselves. All right, so on implicit differentiation, remember that's the kind where you have x's and y's mixed up. So I'm going to say here x's and y's, right? So for example, maybe I want to find a dy dx, right? So I'm trying to find dy dx, but maybe I'm given x squared plus y squared equals 10, right? And so on this one we said no problem, you don't have to solve for y, just jump in and start taking the derivative. So Because there's an x on the bottom, that means x terms I just do normally. So the derivative of x squared is 2x. But then anytime I take the derivative of anything else, in this case a y term, so it's 2y, but then you also have to write down your either y prime or dy dx. I'm going to write dy dx. And then the derivative of 10 is 0. And so if I want to find dy dx, then you would want to go on to solve for dy dx, right? Okay, so that was kind of the basic that we talked about for implicit differentiation. But what if, let's look at this one, what if we think about the type that are in terms of t, like maybe I want to find dy dt. So maybe this time I have something like x squared plus y squared plus t squared equals 5. So remember, it's all about the denominator. So it's the t terms that I don't have to put my extra little notation on, right? So the derivative of x squared, yes, it's 2x, but I have to take the derivative of x with respect to t. And the derivative of y squared, yes, it's 2y, but then you have to do your dy dt. I hope this is kind of refreshing your memory. And then in this case, the derivative of t squared, whoops, I don't know why I wrote my equal sign. The derivative of t squared, yes, it's 2t, but because it's a t, I don't have to write that notation. But one thing we talked about is, well, let's say you forget and you do write the notation. Well, in that case, you'd be writing the derivative of t with respect to t. And if it's dt over dt, doesn't it equal 1? So that's why we said you don't really have to write it if it's a t term. So anyway, and then equals the derivative of 5 is 0. And then in this case, it just depends. If they want you to solve for dy dt, then you would, keep the dy dt and get everything on the other side. They could tell you to solve for dx dt. It's just, they could tell you to solve for anything there. I just wanted you to see that it doesn't have to always be in terms of, what's going on here? It doesn't have to always be in terms of dy dx, right? It could be in terms of t. Okay. So this time, and then of course the basics are the trig derivatives. I'm going to do this. I am going to say something that I would kind of mention is we've talked about how the sine of x, yes, you have to know that one. That is, that's all over the place. Cosine, that's going to be very common. Tangent, that's going to be very common. But then, do you remember which of the other three is the most common? Yeah, the other one is secant. Now, that doesn't mean that you don't have to know cosecant and cotangent. I just wanted you to know that those four were the most common. I wonder if you could fill all those in correctly yourself. So hopefully you remember the derivative of sine and cosine, right? Those are derivatives of each other. And then let's say tangent, that's probably another common one. Remember that is secant squared. And then I'm going to skip down to secant. What was secant? That's the other common one. That one is secant tangent. And then as far as cosecant and cotangent, we're going to mention them because, I don't want to just ignore them. You're supposed to know them. But tangent and cotangent are similar. So if tangent is secant squared, then cotangent is negative cosecant squared. Secant and cosecant are similar, so this would be cosecant cotangent. And you have to know those, you guys. You just have to know them. Okay? And then we actually learned this in chapter 5, this derivative of e to the x. So we know that the derivative of e to the x is itself, right? Derivative of e to the x is e to the x. And we should mention kind of the extended version. If you have, like, let's say e to the x squared. Do you remember the chain rule version where it's still itself, but then you have to multiply by what? Right, the derivative of the exponent. So times 2x. Okay, now number 8, I'm going to go ahead and put it here so we can have it with all these derivatives. I honestly don't remember if we talked about this one. If we didn't, it's one of those things that we'll kind of add when we start talking more about derivatives. But I'm going to go ahead and write it here. And a to the x means, it's different than e to the x. A to the x means, like, what if you have 2 to the x, all right, as opposed to e to the x, or 5 to the x, or 10 to the x. Well, it's very similar to the exponential. So just like e to the x, the derivative is itself, so it is 2 to the x. And the same thing over here, if it were 2 to the x squared, it would be, 2 to the x squared times the derivative of the exponent. But what makes this one different, and I don't think you care about the why, I could prove it, and show you the where it comes from. What makes this one different is then you also have to multiply by the natural log of 2. That's just how the rule works. It's one of those rules that you just have to know. And the thing about this is, in the old days, I would have said, and by the old days, I mean like 2 weeks ago, I would have said, hey, on the AP exam, this might be on there. It's very likely that it's not, but it could be if it is. It's just one question. With the new stuff, I don't know, but I'm not going to sacrifice mentioning it. Okay, so we talked about the basics for derivatives. So if you look at these next 8 problems, like if you look at number 1, very straightforward. That should take you seconds, right? Hopefully you look at number 2 and you see a product rule first, right? A product rule first, and then eventually you'll, don't help me. A chain rule is going to be a part of that, right? Hopefully on number 3 you see a quotient rule. I'm sorry, on number 4 this should say y equals that, right? So there you have a chain rule. On number 5 you're just going to do your implicit, right? So we want the directions to be to find dy dx. I should have written that at the top. Okay, you got a trig, you've got a exponential, whatever. Okay, so you know what? Let's do something. Let's make a little bit of a change here. How about for number 6, cosecant? That's dumb. You're just going to copy what's up above. How about on cosecant? Let's change that and say, why don't you find the derivative of, how about sine squared? Okay, I'll even give you a little hint. You're going to think of it as sine of x quantity squared, right? Okay, so try those. We'll do like we did before. We'll stop and I'll ask you a couple questions about these, right? Once you've tried all of them, then that's when we'll jump back into the video picking up again. Okay, so there you go. This time I don't have the work. I just have the answers because I want to make sure that on these derivative ones I can kind of see a little bit more of your work when you submit. So if you need to pause, then go ahead and pause. But I've just got the answers there. So let's see, just the answers. So this whole thing is the answer to number 2, right? There's your answer. And this whole thing is your answer. Okay, so compare those, see how you did, and once you've had a chance to compare those and check them and try and fix the ones you got wrong, then we'll pick back up with the video. Okay, so when we get into integration, this should seem a little bit more familiar, right? We've done it a little bit more recently. So there's a power rule for integration, and the idea is if we take the integral of some power of x, remember it becomes x to the n plus 1 over n plus 1. And remember the key to these is you have to make it look like a power of x. Like for example, when you first look at, let's say, the square root of x, right? Right now that's not a power of x. You need to think of that as x to the 1/2, right? Before you can actually do the problem there. Okay, so we've got the basic power rule that we learned, and then we have the trig integration. And remember we said on the trig integration you just think backwards, right? So like for example, if you're going to integrate, let's say, the secant squared, then you would go up here on the list and say, okay, well if the answer is secant squared, that means it goes backwards to being tangent, right? So basically on these, we're just going to put down here, think backwards, right? So if you know the trig derivative rules, then you don't have to memorize a whole new set of rules for these. You just think backwards. Okay, now fundamental theorem. Again, we're going to get into this a lot more when we review chapter 4, so I'm just going to give you the basic fundamental theorem, the first version of the fundamental theorem, and that was the one that said, hey, if you have boundaries like from a to b, right? So the integral of a derivative from a to b. So when you integrate, remember you get the original function, and then we would evaluate that from a to b. Remember, that was kind of our notation. And then if I take that one step further, what that means is, which one do I plug in first? Yep, you got it. I plug in b, so it would be f of b minus f of a. So this is the first, most basic form of the fundamental theorem, and we'll develop that more when we review our chapter 4. And then we had the second fundamental theorem, okay, and the basic form of the second fundamental theorem said if you take the derivative of an integral from a constant to x, right, of some function, I'll say in terms of t, but it's probably not going to be an x, then the idea is that the derivative and the integral cancel, and it comes out to equal this same function, but in terms of x. And remember, the key here is it has to be the derivative of an integral. Once we got further into these problems, we did some where it just said, hey, find the integral from 2 to x of, whatever. Well, that's not second fundamental theorem because it doesn't say to take the derivative of it. Okay, and then we had kind of a little bit more involved form of the second fundamental theorem, and that said if you take the derivative of an integral, and this time it goes from a constant to some function of x, right? X squared, square root of x, e to the x, whatever. I'll say g of x, so it's more than just an x, of some function, and I'll say here of t. Then remember this form, it's the same concept where you just plug in that g of x, so it's the f function, but in terms of whatever g of x was. And do you remember what the extra part to this one was? Yeah, then you have to multiply by the derivative of g. So all that is times the derivative of g. So there was the two forms of second fundamental theorem, right? The basic and then the one that was just a kind of a little bit more involved. All right, and then we had all of our lists of u substitutions. So let's just kind of make a list to refresh your memory. The first kind of u substitution we said look for is maybe you let u equal a parenthesis, remember? And that type is, when would you do that? Well, if you were trying to integrate some quantity with an exponent, right? Then you would let u equal the parenthesis. And remember on these you do your u, du, dx, right? So then the second kind we learned was, well, what if you have to do u substitution when there are trig functions involved? And we said, well, you might let u equal ugly angle. And that's the type that when we developed this, we kind of talked about a shortcut. And again, we'll talk more about that when we do more with the integration review. Or we said if there are multiple trig functions, you might let u equal, I don't know why I wrote u equals. You might let u equal one of the trig functions. So you might let just u equal sine or u equal cosine, something like that. All right, so we had u equals a parenthesis. We had what about trig functions? And then the third type was one of the recent ones. We said, well, you might let u equal the denominator. And something I really want to say here, if you're looking at u equal the denominator, do you remember what we said to do? As soon as you decide you're going to try this, before you go through all your du, dx business, we said look and see if it's a u prime over u, because you might be able to integrate that and turn it into natural log of u without having to go through all the work. All right, so you might let u equal the denominator, and then we said, well, as a part of that, if there's a natural log in the integral, then that's the one that kind of trumps all else, right? If there's a natural log, you have to let u equal the natural log. And then we did one last kind. We said, well, if you have exponential functions, and if you have this ugly exponent, you might let u equal the exponent. But you're only going to do that if the exponent is like x squared plus 5. Or even x squared. You wouldn't do it if your exponent were just x, or if your exponent were just negative x. Okay, so that's a crash course on the basics of integration. So we have here, let's see, 11 problems. And kind of look through. I see something. Number 3 has this weird line out here in front. I don't know why it's there, so that shouldn't be there. Sorry about that. So try all the different kinds. Remember, these should not be terribly involved. Yes, there's some u substitution, especially the last several are different kinds of u substitution. But they should be the more basic of the integration that we've done. But again, I know it's been a long time. So try those. I'll kind of ask you some questions on your way through. And then we'll come back and compare. And make sure you come back and I'll give you kind of some final instructions. Okay, so I have some answers here. I'm going to let you compare your answers. Again, if you need to pause, obviously you can do that. I will give you just a little bit of a heads up. I didn't need to do U substitution until I got down to number 5. And that was the type where I let u equal the parenthesis, right? And then I'll let u take it through the du and the dx. And on number 10, we let u equal the exponent. And then on number 6, hopefully you can tell we let u equal the ugly angle. And then on number 11, number 11, we let u equal natural log of x. So I only did u substitution on the last, these last ones down here at the bottom, even though when I'm sorry, on number 7 I did u substitution, right? And on this one you have to decide, should I let u equal sine or should I let u equal cosine? Because one of them will work and one of them will not. Let's see. On number 8, you might have tried to let u equal the denominator, but it was a lot easier to not do all that work and do some manipulation and turn it into a u prime over u. So hopefully that gives you some hints. Once you get these all, corrected and you kind of get things justified in your head, then I want you to submit this whole thing on Canvas, and then let's see. So you'll be doing this on Wednesday. So then we'll be back together again on Friday, where we will dive in a little bit more to the limits chapter, and we'll kind of talk about your online quiz that'll be set up for the weekend. And so again, if you have any specific questions, you guys definitely let me know. There's just different people here and there that I've been able to answer questions through text or email, even kind of jumped on some kind of a video conference, so we could just kind of talk through some together. All right. Good luck with that, and I'll see you, well, kind of, on Friday.